CT scan. CT scan stands for computed tomography. I'll show you what a CT scan device is like. Most of you already know what a CT scan is. So CT scan is measured, or it is obtained in the lab. It is obtained in the surface. We bring rock samples to the surface and we perform CT scan. CT scans are like images. And in this particular project, the goal was to extract, to generate synthetic geomechanical logs from CT scan. So using CT scan, we wanted to generate synthetic geomechanical logs, which estimate or which approximate the subsurface condition. So in the subsurface, there are some geomechanical properties. Let's say we cannot measure them. So the other alternative is you bring rock samples from the subsurface to the surface, you perform CT scans, and from the CT scans, we try to extract geomechanical logs. I'll tell you what I mean by geomechanical logs. So this particular work was done with a service company. I, as a professor, my main job is to find interesting research projects to convince service companies, federal agencies to give us research funding so that we can perform these interesting new tasks. So that's my job as a professor. And most of the development is done by graduate students that work with me. So Yao Kun Wu, who is currently pursuing higher studies in computer science, he was a petroleum engineer, and I worked with him, and most of the things that you'll see is done um, by me and him together, and we showed it to service companies and they found it interesting. So going ahead, what you see here is a CT scan device. This is a CT scan device, computed tomography. There is a rock sample. It's a cylindrical piece of rock. It's brought from the subsurface. These are called whole core. And on this whole core, these are inserted into the CT scan and we perform computed tomography. So what exactly is a computed tomography? Computed tomography is an indicator of density variation in the material. So that's one of the properties. It's an indicator of density variation. This computed tomography machine that you see, it sends high energy radiation. These high energy radiation, they will penetrate the rock. Some of them will get reflected. Some of them will get scattered. So you capture all these energies, and from there, you get a CT scan image, which is approximation of energy which is approximation of density distribution. So what you see here is on the top is a CT scan, a computed tomography scan. It means a lot, but the easiest way of understanding these scans is it's a density distribution. So what you see here in bright light, so anything that's very white, that's where you have low density. Anywhere you see the darker colors, these are where you have more density and so on. So this is the whole core CT scan. What you see here is two different angles. So we measured the whole core at 0 degree and then we turned it. So these are the azimuth. So we perform CT scan at 0 degrees and 90 degrees, and that's what you see here. These are all 3D scans. So if you look at this CT scan, each scan is made of slices. There are, if I remember correctly, there are close to 40,000 slices. Each slice, if I remember correctly, each slice is close to 2000 by 2000 pixel. So there are 40,000 pixels. Sorry, there are 40,000 slices. These are slice. We combine the slice to get the whole core CT scan. Each of the 40,000 slice is 2000 by 2000 pixel. So this entire data set was close to around, I think, 35 to 40 GB. Okay, so these are CT scans. This CT scan that was done on 90 feet of rock. So on this 90 feet of rock sample that you see, CT scan was performed. There were 40,000 slices. Each slice was 2000 by 2000 pixels. And there were in total 35 to 40 GB of data. And the objective of this entire work was to convert the CT scan, these images, convert these images into geomechanical properties. So what do I mean by geomechanical properties? We have horizontal Poisson's ratio, vertical Poisson's ratio. Those of you who are from geophysics background, all of you are comfortable with Poisson's ratio, Young's modulus. For petroleum engineers, maybe you are hearing these things for the first time if you are, let's say, in second year of your petroleum engineering, or if you are sophomore, but I'm pretty sure at junior and senior, at third year and fourth year, you know already what a Poisson's ratio is. So this is an important geomechanical property. The other one that we wanted to generate was uniaxial compressive strength. It's also written as UCS, bulk density and effective porosity. So these were the 5 important targets. Let me write the word target. These were the 5 important target. To generate these 5 targets, we need an input. And the inputs were CT scan images. Each image is 2D. A combination of 2D images is this cylinder, but each image is a 2D slice. So from a CT scan, which is the input, in machine learning, in data-driven world, inputs are also called features. So we have features, and from the features, we want to generate targets. You see permeability here. Service company wanted us to generate permeability, but we knew that we cannot generate permeability that well because a CT scan is an indicator of density variation or compactness of the material, how tight the material is, how consolidated the material is. So from a CT scan, it's very difficult to get permeability. We knew that we cannot generate permeability that well. Despite that, we kept it. So my main focus is not permeability here. We couldn't generate it properly because CT scan is very weakly correlated to the transport property. But what you'll see is we were able to generate Poisson's ratio and effective porosity, I think, pretty well. Uniaxial compressive strength was difficult to generate. So this entire talk after this is focused on what is the right way of converting the features that you see here, this whole score CT scan. How can we convert it to target? That's the main objective of this entire set of slides. So I'll take a short break. Ask me questions. Anything that bothers you, feel free to unmute and ask if you want to, or leave it at the chat. A short break, and then we'll move ahead. I told you the objective.
So hi, Professor. I am George. You know me from me,
Yeah,
right?
we know each other. Yeah.
Yeah. So my question is, so in this case, you had like two cores, right? Or one core, right?
So this was a 90 feet rock,
Okay.
90 feet cylindrical rock, 4-inch in diameter.
Uh-huh.
And there was only one. What you see there is so when we perform CT scan, it's a 3D scan. So it contains 2D slices and you combine all of them and you get a 3D volume. So what you see there is at 0 degree and at 90 degree. So we just had one whole core, which was 90 feet long and 4-inch in diameter.
Okay. So in this case, you calculated these properties based on the pixels of each uh, slice.
Pixels, yeah. So there are 40,000 pixels, and from these 40,000, sorry, there are 40,000 slices.
Right.
Each slice has 2,000 by
2000.
2,000 pixels. So how much is that? That is, I think,
Uh, we need
yeah,
to multiply
four,
all of
four,
that.
yeah, I think 4 million, something like that. Yeah,
It's
yeah. So each slice contains 4 million pixels.
okay. So in this case, I think you have applied some.
Downscaling is required, feature
Yes.
extraction is required. So
Yeah.
that's the
Yeah.
whole goal. Plenty of times what you'll have, and that's a
Right.
great question. So what you will have plenty of times in oil and gas is you will have a very high resolution feature, which
Right.
I have. Feature has very high resolution, it has a lot of data, it has a lot of information, and that's what you will generally have. And your target, which is over here, target will be a low resolution.
Yeah.
So here, the targets that we are trying to generate, they have a low resolution. What I mean by that is each point that you see here, so it contains points, and each point that you see here is at zero point
Combination.
0.5 feet.
Uh-huh.
It's very difficult to generate this particular target higher than this resolution because we are doing a data-driven modeling. In data-driven modeling, we need to learn from the data. And the data that we had as target, that itself had a low resolution. And the resolution was zero point 0.5 feet for the target, which is the output, and a very, very high resolution input. Because at the surface, you can measure anything at highest quality and highest resolution. So that's a great question, George.
Thank you.
Yeah, that kind of clarifies a lot, which I couldn't mention clearly. Okay, anything else?
Hello, Professor. This is Zishan from Saudi Arabia.
Hmm.
My question is the target parameters that you have, from where did you get these parameters? From experiments or from some
Yeah,
models?
yeah. So all these parameters were obtained from sonic logs and NMR log. So for a well, uh, first somebody obtained the 90 feet rock sample, 90 feet rock sample. So somebody was drilling, and in that drilling process, that 90 feet of rock sample was obtained. It was taken to the surface, it was measured. And once that hole is created, uh, NMR logs and sonic logs were taken down, and these things were measured. So right now, to the best of my knowledge, there is a lot of experiments that we are doing in terms of data-driven modeling or data science in oil and gas and in many other industries. A lot of things are still unknown. So when this project was funded, which was almost 1 year back or 1.5 years back, the service company that I was working for in this collaboration, they had this question of how well can CT scans be used to predict subsurface properties. So, so that's why we needed surface data and subsurface data for the training. If you train it well, if you train it well, then in the future, you will not need the subsurface data. Using the surface data, you can generate subsurface logs. So that can save money. That can help you speed up your analysis. Okay. So in this particular work, I'll show you the training process. If the training is successful, all we'll need is a surface data, which is CT scans. And from these CT scans, you can generate these subsurface properties. So that's
Thank
why
you.
I use the word in the talk, synthetic. We are trying
Yes.
to synthesize. These are not original. These are like backup. Using these synthetic, you can better decide where to measure, what to measure, and so on. So this particular investigation was a proof of concept investigation, and we the biggest problem was what's the right workflow for doing this task. Okay,
Okay, thank you.
so let me go ahead. Let's move to the next part, which is uh, so talking about the features, which are the inputs in data analytics in machine learning. Generally, inputs are referred as features. They are also referred as attributes. Very rarely people use the word inputs. Input is not that common. Generally, people use features or attributes. So because we measured in the surface, we had 44,700 samples in the surface. We have all these CT scans that you see here. Because these whole cores are slabbed, you slab it. You divide the whole core into three-fourth and one-fourth section. So because you cut it, that's why you only have this as your image. So what you see here is one CT scan image. It has information of how the density is distributed in that particular image. In addition, the service company that I was working with, they used their own computational models to generate photoelectric factor, density, clay content, sand content, limestone content, content of high density material, and porosity. The service company, they generated these 7 CT derived properties from the CT scan. They have an inbuilt algorithm. It was not a machine learning work. It was a uh, inversion type of work, which is physics driven. So for each slice, they could generate photoelectric factor, density, and so on. So 7 CT derived properties were also generated by the service company. These CT derived properties are also features. So you have these CT scans. You can use the CT scan or you can use the CT derived property. Both of them are features. If you look at this data, this is a very high resolution data. At every 0.002 feet, there is a CT scan slice. And for that CT scan slice, we have these 7 properties. All of these are input features. Going ahead, in terms of target, we have 181 samples in that 90 feet. If you look back, this is also 90 feet. For the same 90 feet, we have 181 samples that were measured in the subsurface. Because it was measured in the subsurface using downhole logs, they have poor resolution, 0.5 feet. You cannot attain a very high resolution in the subsurface. It's very difficult because there's a small hole. In that hole, there's a lot of environmental noise, and you can only put limited amount of sensor, and using that sensor, you have to measure. So it's not that easy. And because of that, subsurface data, which is the target, has a lower resolution for our case. We have horizontal Poisson's ratio, vertical Poisson's ratio, uniaxial compressive strength, bulk density, and porosity. This is effective porosity. We had permeability, but we can ignore permeability. We didn't do a good job in predicting permeability. Okay, so now let me show you the method, the approach. Personally, I learned some interesting things, which is very important to ensure that you have a very good data-driven model. And that's one of the reasons why I'm sharing this particular talk, because if you develop a data-driven model, I want most of you to remember some of these things that I learned. So I'm kind of sharing those with you. The first thing is perform exploratory data analysis. There are a lot of different ways in which you can perform exploratory data analysis. What you see here is one example of exploratory data analysis where we are looking at the relationship between the targets and the features. Anytime you see a lighter color means the feature is strongly correlated to the target. That's what it means anytime you see the lighter color. If you see the darker color, feature is weakly correlated to the target. And what you see here is mostly we have darker colors. Now, one thing that I want to share with you is we are using one type of correlation. This is called Spearman rank correlation that looks at nonlinear variations or nonlinear correlations. There are a lot of different ways in which you can look at these correlations. There is Pearson's, there's something called, let's say, Kendall's correlation. Some of them are for categorical data, some of them are for continuous data. Here, the target is continuous and the feature is continuous. Continuous in the sense these are numbers. These are not what you call, these are not um, categories. These are not groups. These are numbers. So because they are continuous, Pearson and Spearman are pretty good ways of looking at correlation. One thing that stands out here, if you look at these plots, if you look at target, row B has around 0.6 to 0.5 correlation with mean PEF, mean density, and mean clay. These features were derived from CT scan. Who derived it? The service company derived it using physics-driven models. So this is what you see. We did a lot of different correlations that helps us better prepare our remaining workflows. So just going ahead, um, I won't stress too much on these takeaways. That's not that important right now, but all these different types of correlation helps us better understand how is our target related to the feature. So now comes an important step, which is cleaning your data. In any data analytics or machine learning work, I think around 50% of time, 50% of time, to the best of my knowledge, based on my experience, 50% of time goes in cleaning the data. 40% of time goes in evaluating your model, evaluating the model. So the remaining 10%, which is in between, is where you develop the model. That's what I have seen in most of my projects related to data analytics and machine learning. Data cleaning takes a lot of time. If your data is not cleaned properly, it is a waste of time to do the rest of the things. And when I say data cleaning, the right word should be data pre-processing. And in data pre-processing, there are a lot of things, and I'll share with you, I think, 3 things in data pre-processing. It's very, very important. There are a lot of different things you can do in the data pre-processing, and it takes close to 50% of your time. Then you have model development. Model development takes 10% of times. And at the end, see, it takes 10% of time because most of the data in oil and gas are smaller data. If you work on, let's say, terabyte of data, then your model development will take a lot of time. Because we work on smaller data sets, that's what I've seen in most of my projects, it takes only 10% of time. And the final step is evaluating. You will develop a lot of data-driven models. These data-driven models, they can relate anything to anything. You give it any feature, you give it any target, they will relate it. These data-driven models are complex. They are like functions. They can find all the different functions, crazy mathematical ways of relating features to target. So there is nothing in to my knowledge, there is nothing extraordinary in developing the model, which means relate the features to the target. It's very easy. There's nothing magical there. What comes after that is very important, which means you have related the features to the target. You have related them using a model. You have to evaluate the model. So a lot of time goes in evaluating the model so that you're confident. Okay. So I'll show you this particular slide and then I'll take a short break where we can have a discussion if you want. In this particular slide, what I'm emphasizing is how I performed pre-processing. And there are a lot of different steps in pre-processing. Here, I'm just doing two things. Step one that I'm doing is I'm improving the quality of the data. How am I improving the quality of data? By removing CT scans that have poor quality. I have 44,000 CT scans. I'm removing the scans that have poor quality, and I'm removing the boundary effect. See, depending upon your data, you have to decide how to improve the quality. For my data, which is CT scan, the boundaries are where things get corrupted. So I have to remove the boundary effect. So these are two things to improve the quality of the data. These two things can be called as data cleaning. And after that, I'm performing feature extraction. To the best of my knowledge, without feature extraction, you cannot do anything. Raw data will never solve your problem. You have to generate, as I always mention, you have to generate informative, which contain information, relevant, independent. You have to generate features that are informative, relevant, and independent. And that's only when these features that you have generated will help you develop your model. Without feature extraction, your models will not be ready. I will show you what type of feature extraction I used for this particular task. Do you have any questions so far?
Hi, Dr. Misra. This is
Yes.
Deborah from Texas A&M.
Yes. We had
I
an
got a
email exchange recently. Yeah. Tell me.
yes. Thank you for that. I appreciate it.
Yeah.
Yeah, I have a question regarding the resolution of the city. I know you already talked about the pixels, but in terms of kind of like in metric, do you mind to comment on how much micron it can get in a pixel?
Okay. So see, again, we are just approximating. I don't exactly remember. Uh, 2000 by 2000. Okay. Each slice is 2000 by 2000. Okay. And these are pixels. And let's say there is a whole core CT scan. So this whole core CT scan has a diameter of 4" approximately. So each pixel is 4" divided by 2000 2000 pixels approximately.
All right, sounds
So
good.
how much is that? Yeah, pretty small,
Yeah,
right?
right.
Around 2 to the 2 into, yeah, let's say 10 to the power minus 3 inches. So each side is approximately 0.001 inches.
Thank you.
Yeah. Anything else? Anyone?
Yes, doctor, this is Vishan again.
Okay.
You said that you remove the poor quality scanned images,
Yeah.
but I have a question that since you had 44,000 CT
Hmm.
scanned images, so
Hmm.
did you develop any code to remove poor quality images
Yeah.
or by
Yes.
visually?
Yes.
And
So
was the factor of what was the judging criteria for the quality?
yeah.
Were you looking for the noise or?
Yeah, so there are a lot of different ways in which you can define poor quality image. And my recommendation is always try to automate, because that will help you. If it doesn't help you in project 1, it will definitely help you in project 2. So always try to automate. Automation can be difficult, but once you automate, life becomes very easy. Uh, Learning to automate is an art. So the more you do it, the better you get at automating. So always automate. And coming back to your question, I'll just show you the poor quality image. Look at this. So the way I define poor quality image is where things are broken. Things are broken like this. So how do we define a poor quality image? So for all this work that I have done in the last 6 years, I always use different packages in Python. I don't use R, which is another language. I generally use Python. And there are a lot of different functionalities in Python. One of the packages is skimage. There is another package called CV2. In skimage, there is a simple function that can count how many clusters, how many broken islands, how many different regions you have. So let's say we run that algorithm. It says there are 4 clusters. And we run another algorithm which says that the volume fraction of the white phase, the volume fraction of the white component is, let's say, less than 10% in this entire image. So we had some criteria to look for. We looked at how much was the rock broken, what was the volume fraction of the white phase, and that's how we defined which of these slices were not useful. And we removed. So if you look over here, we randomly selected slices which are high quality after we remove the poor quality. So anytime we select any random slice, everything looks intact. Everything looks one piece. There are some broken fragments here, but that's fine. So overall, there were yeah, let's ignore this. Let's go back to where we were. So Jishan, I hope I answered your question, right?
Thanks, doctor.
So poor quality means anything that's broken, anything where we don't have enough information about the rock. Out of 44,000, we remove 10,000 such slices.
Okay.
So there is a question on the chat. Good morning. For the pre-processing, are you using a specific software for pre-processing? So as I mentioned, I use Python and Python packages. And the easiest one for you to start, if you're interested, skimage, image, and the other one is CV2. You will have to install it. And once you install, you can do a lot of interesting things with it. There are a lot of advanced packages. These are just the starting point. This is a direct measurement of CT scan or a derivative from other properties. Maybe Sergio can ask me that question later on. Okay, so let's see. So
Professor Misra?
Yeah.
Oh, I had a question over. So you mentioned making when you're forming the models, when you're forming these equations using the program, is there a way to generalize these models over like a certain population of data sets, or how do you really solve really large data sets, or does this already account for large data sets?
So when I was talking about features and targets, right? Features and targets, you're trying to map it, you're trying to relate them, right? Is your question related to that?
Yes. So because you mentioned the correlations. There's some things that have like very small, low correlations. Some things have very slightly higher correlations.
Yeah.
And when you build these models, how can you like generalize this on, for example, like a larger picture. That's my question.
Yeah, so generalization is very difficult. If I understood your question properly, let's say your feature is, let's say your feature is permeability, porosity, and saturation, and your target is, let's say your target is uh, uh, lithology or the mineralogy. So you have three features, you have one target, you developed a model, the model relates, but then if you have a fourth feature, that model will not work, right? If you have permeability, porosity, saturation from a carbonate reservoir, but you trained everything on a sandstone reservoir, it will not. So just remember this. If you want to build a data-driven model, which generalizes well. So the word that Farooq used, and that's the most important word in any data-driven world, is generalize. So that's why I'm writing it in capital. I hope I got the spelling correct. Generalize. Yeah, I figured out I was doing something wrong. So that's what you want. You want a model which generalizes well. And what does it mean when I say generalization? It means that whatever you have developed works well in future when you don't have the target. Most of these work that we do is we are trying to relate feature to the target. And why are we doing it? Because in future, we will not have the target. So how can we use the function that we have developed to keep on generating target when the target is not there? So that means you're performing a task. In order to do this for future, you need a model that generalizes well, as Farooq mentioned. And for generalization, what you need is when you are training your model, your feature and your target should have all the different statistical distributions, all the different statistical relationships in it, which can occur in future. If there is a particular statistical pattern that is not there in your training data set, you can never predict that statistical distribution. Your function that you have created using data-driven model, it can only predict those statistical distributions, those statistical patterns that it has seen in the training data. So Farooq, I hope I answered your question.
Yes,
With
sir. You did.
so your goal when you create your training data set, your goal should be to get as much statistical information, all the different statistical variables as possible. And in today's in this particular set of slides, I'm just showing you a little bit of data. Why? Because of proprietary reasons. There are a lot of things that the company doesn't want to share. So this is a simple thing that I'm sharing with you. In real world, these applications require more and more data. That's why they're called data-driven models. What's the advantage of data-driven models over physics-based models? The biggest advantage is generally physics-based models, they take into account first order relationships. Generally, they cannot take into account a lot of complex relationships. If you want to handle a lot of complex relationships, then your numerical simulator will become more and more computationally cumbersome, or they will become computationally expensive. So instead of using physics-driven model, we use data-driven model with a hope that these data-driven model can understand some physics, which simple physics-based models cannot understand. So that's why we as engineers, scientists, we use a data-driven model to discover or to capture some physics which cannot be captured in simple physics-based models. Darcy's law is a simple physics-based model. It has a lot of assumptions. because of those assumptions, Darcy's law will not generalize well. So instead of using Darcy's law all the time, we can also use data-driven model, which can do better than Darcy's law as long as the data that it has seen is reliable. Okay, so any other questions? We are, yeah, let me go ahead. So let's see, we have almost 10 more minutes. That's fine. I'm not in a rush in the sense my whole goal is to share some of these interesting things. If we cannot complete this set of slides today, my whole goal is to have more sessions like this so we can slowly kind of understand some of these basics as we proceed. So I'll just go ahead. Workflow step 1, remove poor quality, perform feature extraction. This is part of pre-processing. After you pre-process, we perform multiple train test split. Generally, what we perform is a single train test split. In this case, I'll be performing multiple train test split. Why? Because I have a limited data in this demonstration. So for this demonstration, because I have limited data, I'll have to perform multiple train test split. I'll show you what I mean by that. So once you have multiple train test split, your training data set is ready. On this training data set, you will have to perform scaling. What is scaling? Let's say there is permeability that goes from 0 to 1000. There is porosity that goes from 0.05 to 0.25. And there is, let's say, some other property, let me call saturation. Saturation goes from 10% to 60%. So what I mean by scaling is I'll transform permeability, porosity, and saturation such that each of them kind of fall within the same range, approximately the same range. So for example, permeability will now fall between -2 to 2, porosity will fall between -3 to 4, and saturation, because of this scaling, will fall between -5 to 10. So scaling is a way of transforming your data. We generally scale features. We never scale target. If you want, you can scale the target, but I have never performed scaling of the target. Scaling is generally performed on features, and the whole goal is to bring your features into the same range. In the scaling, sorry, in this step, you can also perform something called transformation. So what is transformation? Let's say there is a statistical distribution of a feature like this. There is another statistical distribution of a feature like this. What transformation will do is it will convert the two features into more Gaussian-like distribution. So transformation is converting a feature distribution into Gaussian-like distribution. I have not performed transformation here, but this is something that you should also pay attention. What I have performed here is scaling. Once you scale your features, this is no more permeability, porosity, and saturation. These are scaled permeability, scaled porosity, and scaled saturation. So scaling is what was done first. After the scaling, we reduced the dimensionality. Okay, remember, we started off with raw data. From the raw data, we performed feature extraction. When we performed feature extraction, we generated 214 features. This feature extraction was done on CT scan images. So on each slice, we performed feature extraction and we generated 214 features. Remember, these features should be informative. How will you check for informative? You will look at correlation between uh, the features and the target. They should be relevant. For relevance, you need to have your domain knowledge. You have to understand the statistics. You have to understand what this feature extraction does. And that's how you know whether it's relevant or not. And finally, these features should be independent. When we generate 214 features, out of those 214 features, maybe 80% of the features are dependent. If you have dependent features, it will make your model non-unique. It will make your model weak. So that's why we need independent features. When I generated 214 features, there's a lot of dependence. So that's why I need dimensionality reduction, which I'll show you in the next slide. When I performed feature extraction on CT scan images, I generated feature set 1. When I performed feature extraction on CT derived properties, remember I showed you CT derived properties, which was given to me by the service company. When I performed feature extraction on those, I obtained 35 features. So there are two feature set 1, feature set 2. I don't know which one will perform well, so I'm trying different combinations. A lot of data science is, or sorry, a lot of data analytics, machine learning is hit and trial. You have to try a lot of different things. So that's why you need a lot of patience. Sometimes it can get very, very frustrating. So the whole goal of dimensionality reduction that I'm showing you here is to improve independence of feature. I want features to be independent. So when I perform dimensionality reduction, 214 features will be reduced to, let's say, 30 features. And these 30 features will be independent. So that's what I mean by dimensionality reduction. Dimensionality reduction is also performed on features. Scaling is performed on features. Generally, we don't do anything on the target. So when I perform dimensionality reduction, let's say I have feature 1, feature 2, feature 3, feature 4. This is done after scaling. The first thing I look for is there a strong linear correlation between feature 1, feature 2, between feature 2, feature 3, and so on. So that's what I look for, linear correlation. For this, I need to look at Pearson's correlation. This is one way of looking at linear correlation between features. If there is a feature which is highly correlated with another one, if F1 is highly correlated to F2, then I will not use F2, I'll only use F1. If F1 is highly correlated with F3, I will not use F3, I'll use F1. If some of you are thinking, why am I not using a lot of features? Then I can answer that, but I'll wait for that. If there is a question like that, I'll answer it. But feature reduction, dimensionality reduction is very, very important. So first I remove linear correlation between, oh, okay, sorry, I did a mistake here. So
I was just seeing like your first point, because you said remove features linear correlated with
targets,
targets.
yeah. So wait a second. So yeah, so what I was just explaining is for this part, the third part, remove highly correlated features, and I'm removing highly correlated features using Pearson. So this is step 3 that I just explained you. Regarding step 1 in dimensionality reduction, there are a lot of features, F1, F2, F3, and F4, and there's a target. So the first thing I do is I try to figure out which of these features have strong relationships with the target. There are a lot of different ways of looking for strong relationships. one of the ways that I figure out strong relationships, I encourage my students to look for is look at p-value and look at mutual information. Mutual information looks at non-linear strength of relationship between the feature and the target. It looks at one feature and one target, another feature, another target. It looks at one feature and a target one at a time. So it's looking at all those combinations. So mutual information looks at nonlinear strength between feature and target relationship, and the p-value, which is sometimes also referred as f-test, looks at linear strength between feature and the target. So step one is look for linear strength between feature and target. If there is something that is weakly related to the target, remove it. Then look for nonlinear strength between feature and target. If something is weakly related to the target in a nonlinear way, remove it. I remove features if they don't have enough information contributing towards the target. And for that, I use p-value first and then mutual information. So step one, step two is looking at features and target. Step three is looking at only the features one at a time. Sorry, one pair at a time. I'm looking at pairs. And finally, what I do is, let's say I have 50 features to begin with. Using step one, step two, step three, I reduced it to, let's say, only 10 features, feature 1 to 10. The final step is I look for whether each of these features, do they have enough variance? Do they have enough change? If a feature is just a constant line, or if the feature only changes a little, then I'll remove it. But that's my final step in dimensionality reduction. Why am I performing dimensionality reduction? Because I want to have independent features. I don't want 100 features. If I have 100 features, then the problem is there's a lot of problems. Model will be non-unique, which means it will not generalize well. It will be computationally expensive to train something with 100 features. Anytime I see my students working with 60 features, 70 features, I tell them, please don't do it, because it's the model is non-unique. It's computationally expensive. Memory, there will be problems with memory. You cannot store a lot in the RAM and then process. And overfitting. Overfitting is a big problem, which means you will get amazing performance on training. Sometimes you'll get very good performance on the testing data, but then when you'll go out and apply it on the real data in future, you will not get anything meaningful. Why? Because your models were overfitting. Why were the models overfitting? Because you had too many features, and these features are not independent. So I think that's it for today. We can have a little bit of discussion, and maybe in future, I'll try to complete this set of slide deck. Daniel, when are we meeting next? Or Kayla? If you're muted, you can unmute. If you're gone, that's fine. Kayla is there. She's recording. She had a lecture.
We are going to meet the 26th of
Okay,
October.
26th. Yeah. So the goal on 26th is image analysis. And one of the things which is important in image analysis is feature extraction. And I'll show you what kind of image analysis I perform on these CT scan slices. And I'll also show you some other examples of image analysis in our next meeting, which is on 26th October. Am I correct, Kayla?
Exactly. We will send a link with all the information again.
Yeah.
But yeah, it's the 26th.
Okay, great.
Yeah,
Any
next week.
questions?
I have a
Sir,
question.
Yeah,
I
go ahead.
also have a question.
Go ahead.
This is Peace from Texas A&M. So my question is, in the case that all your features have a weak relationship with the targets, how do you handle this and how does it affect your model?
So all the features have weak relationships, right?
Yeah, with your target.
Yeah, yeah. So in this particular task, I'll just jump. mm, let's see if I can jump ahead. Yeah, it's a long jump. Okay, let's see over here. So which one should I focus your attention to? Just look at this one. So this is just one instant. This is just one instant. This is not valid for the entire task that I'm performing, but what you see here is a target, and
I don't think you change your screen.
that's
Wait.
strange. I see the screen has changed. Do you see the screen?
Oh. I
I can see the screen.
Oh, I guess it's my internet then. Okay.
Do you see that when I'm writing?
No.
What about the rest? Do you see the
We can
screen?
see it.
Can't see.
Yes,
I can't
yes,
see.
Yeah, we can see.
Okay, okay. So I'll just answer this thing that. So what I'm showing you in this screen is there are only 7 out of 35 features that have enough information or enough strength in terms of their relationship with the target. There are only 7 out of 35. And that's what it is. In most of your work, you will see only few that have enough strength. If you don't have enough strength, then what it means is those features are not suitable to develop data-driven model. So what should you do? You should use other feature extraction techniques. There are a lot of different ways in which you can extract features. And in the next slide, or in the next seminar, I'll show you some feature extraction techniques that are very good for images. What do I mean by feature extraction? Let's say there is a data which changes a lot. I've just drawn a data on the slide. It is changing a lot. Instead of using all that data, which is raw, what you can do is you can use a mean or an average of that data. Or let's say you can use the standard deviation in the data. This is just one simple example of what I mean by feature extraction. Instead of using the raw data, you're using something more meaningful, which is, let's say, an average or a median. So which feature extraction techniques are the best depends on the task. So coming back to the question was, I think, what should be done if you don't have enough strength in the relationship between the features and the target? If that's the question, then my solution is try other feature extraction techniques. If that doesn't help, then maybe your data that you're using was never good enough for your task. These are data-driven models. They can only work if you give the models, the functions, good features. Your model is as good as the features you give it. Okay?
Okay, thank you.
So most of you have heard about neural networks, right? Neural networks, and a lot of people have a lot of good things to say about neural networks. Just a second. So a lot of people have a lot of good things to say about neural networks. Personally, I never had a good relationship with neural networks. Personally, I never had good performance coming out of neural networks. Why? because most of my data sets are small. Most of the times I have a lot of features in the data set. So there are a lot of features, but the size of the data, what I mean by that is the number of samples in the data, they are not enough. For a neural network to work, you need at least 10,000 samples. And when I say 10,000 samples, I don't mean repeating samples. I don't mean samples which are very similar. I mean distinct samples. In oil and gas, in subsurface world, we don't have enough data. Uh, if you want 100,000 independent samples, then Facebook, Amazon, these are the best places to get these samples. Why? Because when you go to an Amazon website and when you click on the right, you click on the left, and then you wait for 5 minutes, and then you do a double click. And then, so all these things that you're doing on a website, it is captured. And as it is captured for you, who is on the Amazon website, you are one sample. And whatever you do is the feature. So Amazon website has, let's say, 10 million samples each day visiting the website. So for Amazon, neural network is very good because there is enough samples. There is, let's say, thousands of features per sample. Neural networks, they work well when you have a lot of samples. And the reason they work well is because they have a lot of layers. In each layer, you have some neurons. What are these neurons? These neurons are AX1 plus BX2 plus C, where X1 and X2 are the features, A, B, and C are the weights, and whatever you get, AX1 plus BX2 plus C, that entire thing goes through a sinusoid function. It's either 0 or 1. It is either 1 or -1. So each neuron generates either 0 or 1 or -1 or 1, and the input, whatever input you have from the previous step, whatever output you have from the previous step, goes as an input to each of these neurons. So the beauty of neural network is by having so many layers, it does feature extraction on its own. It does automated feature extraction. It can only do automated feature extraction because you have given it 100,000 samples or 1 million samples. In oil and gas, we don't have so many samples. In oil and gas, if we design our own feature extraction using meaningful statistical methods or meaningful mathematical transformation, those are more reliable than trusting on neural networks. Okay, so why neural networks are popular? Because they can do automated feature extraction. They can only do automated feature extraction only when you give it a lot of samples. Okay.
Dr. Misra, I have
Yes.
one question regarding the last slide that you have presented. Can you
Yeah.
come back? And it's also related to feature extraction. Yes. Have ever, I mean, of course you have, but like you are performing a lot of feature extraction, but we have a technique called penalized models, right?
Mhm.
So what do you think about penalized models? I mean, do not perform feature extraction and use penalized models like Reach or Lasso. Uh, what is your opinion about
Yeah.
this with like the data that we have in oil and gas?
Yeah. So, this feature extraction is what I'll talk about in the next seminar. And when I say feature extraction, which I'll talk about in the next seminar, it is all about converting raw data into features. Raw data is useless. You have to extract features, and you can only extract features by
Right.
performing feature extraction. And what you just
Yes.
mentioned,
But how about the
penalized.
next slide? Yes,
Yeah.
yes.
So when
Right
you
there.
mention penalized or regularization, which is what is called,
Right.
you're applying penalty to the model, or you can perform, it is also called regularization. So what's the goal of regularization? Your goal is, if you have 100 features, by performing some penalty on the model, you will only use, let's say, 20 features instead of 100 features.
If you are using lasso, right? But if you use reach, you can, I mean, at the end of the day, you are going to use all of the features, right? But the coefficient is going to be really small for some of them, right?
Yeah. So, so regularization depends on, sorry, regularization is a method, in dimensionality reduction. What I showed you here are methods of performing dimensionality reduction by looking at feature and target. So step 1 and step 2 are ways in which you look at features and target to perform dimensionality reduction. When I showed you step 3 is where you look at features and perform dimensionality reduction. Step 4 is where you look at only features and then you perform dimensionality reduction. So these are a lot of different ways in which you
Yes.
can perform dimensionality reduction. And what you just mentioned, lasso, ridge regression, they look at feature,
Features and
they look at the
features.
target, but they have a model in between. So this is another way of reducing features,
Yeah.
right? So there are a lot of different ways in which you can do feature reduction. And
Yeah. I was
uh,
just go ahead. Sorry.
yeah, so the reason I didn't use lasso here or ridge is because when you use lasso or ridge, generally what you assume is there is a linear relationship between
Right.
these two. And you have a model, so it will take time to build it. So I could have used it. That's a great suggestion, but I have not used it here. Maybe that can be used right between step 2 and step 3, where you perform regularization.
Mhm. And
Hi,
like,
hello.
uh,
Just
go
this
ahead.
is Alejandro Primera. Thank you
Hi.
very much for the presentation. It's quite interesting. Um, a couple of questions. I think you mentioned the model that you're using either Lasso or Reach, or did I get that wrong? And the other question is, how small is the data set? I mean, how many data points you have in order to perform the training? And which cross-validation technique are you using? Thank you very much.
What's your first question, Alejandro?
The
First
model
one.
that you're using, just simply the model that you're using, the
So
cross-validation technique.
for this
Yes,
task,
yes, exactly.
so my answer would be you have to wait for the next seminar, right? As in, I don't
Okay,
want to create
okay,
any surprise, but again, we'll discuss those. So, and I'll answer your question right now in the sense, see, what I do is I use all the models. Why? Because why not? So that's what I do. I
perfect.
use all the models. And then out of these models, some of them are the best. And in this case, depending upon the target, so for one target, Elastic Net was the best model. For the other target, Random Forest was the best model. In none of the targets, neural network was the best model. In all the work, neural network was the worst model. Why? Because we didn't have enough data. So in this task that I'll show you, in this task, we had 180 sample in the demonstration.
I
In the
see.
real world, because we are not showing you the whole data, I'm not showing the result on the whole data. Result on the whole data was much better. So generally what I do in most of my work is I generally have access to 10,000 data points, 10,000 samples. In this case, I have access to 180 samples. Why? Because this was the constraint because of the target. As a feature, I had 44,000. But that doesn't matter. No matter how many samples you have as the features, as the inputs. That doesn't matter. What matters is the target, and we were constrained by the target, which is coming from the subsurface. And for this demonstration, I have only 180 samples. In real world, generally all these things occur or they are performed on 10,000 samples. And then there was a third question, which is
the cross
validate
validation technique.
yeah.
Yes.
So now the cross validation technique depends on the size of the data, right? So because I have such a small data, there's no, I'm using k-fold and I'm using 3 folds. I cannot use more folds because I have such a small data. Because in this demonstration, because I'm using a small data, I'm performing a multiple train test split. And I'll tell you in the next discussion why I think multiple train test split is a much better way of handling smaller data sets.
Yeah, yeah. I'm thinking that perhaps boosting might be a good cross validation technique to be precise of the sample.
Okay.
Thank you very much.
Take
Hey, do you
care.
have time for a few questions?
Yeah.
Okay, this is Peace. So what if you run your model and you look at the metrics and you get a, I guess, deceptively good results? How do you check that you're not overfitting or underfitting?
Yeah. So as I mentioned, 40% of your time goes in evaluation, right? 40% of time goes in evaluation. And uh, so one of your, so let, yeah, somebody drew something here. I don't know who that was, but yeah, that's fine. I didn't know that you can draw while I was presenting. So, uh, you know, let's say you have a model which performs very good and you apply it on the training data set. Anything that you do on your training data set is called memorization. And once you see a good memorization performance, you will apply it on the generalization, on the test data, which is called generalization. Here, you need to define how you will evaluate the model. Will you use R square? Will you use mean absolute error? Will you use root mean square error? Or will you use mean absolute percentage error? In this case, mean absolute percentage error for us seem to be a good metric. I'll tell you later on why the MAPE is slightly better. In most of your work, mean absolute error will be a much better metric. It's a very simple metric. It's looking at errors that you're performing or you're generating for each sample. So anything that you do on training is called memorization. Anything that you do on testing is called generalization. A good model is one where the difference between memorization and generalization is small and both of them are large. So the performance in both memorization and generalization is very high and they're very similar. If there's a big difference between memorization and generalization, that means overfitting. Is there anything else that you can do to know whether you are overfitting your results or not? Um, you can, so there's something called perturbation. You can perturb your data. Perturb in the sense you can add a little bit of noise to your data. And a good model is something that is very less sensitive to noise. If you add a Gaussian noise to one of your features, then your target shouldn't change that much. There are a lot of ways in which you can test for how good your model is. For me, it's mostly looking at the difference between memorization and generalization, and then adding noise to some of these features and ensuring that the prediction doesn't change too much. A good model shouldn't be very sensitive to noise. What is overfitting? Overfitting is when you have learned or when you have memorized the noise in the data and you don't want to do that.
Okay, thank you.
Okay, so I think that's it for today. It's already, was the time 12:22. So we'll meet again on 26th. Thanks a lot, Daniel
you.
and Kayla.
Yeah,
Thank
thank
you.
you. Thank
Yeah,
you.
Kayla was patient
Thank
for
you.
organizing this.
Thank you,
And
Dr.
she has
Misra, for your
recorded the
time.
video, and hopefully those of you who couldn't attend can look at that video. Kayla,
Definitely.
let me know when you upload this video, okay?
Yeah, definitely. I will
Yeah,
do. We will
the
send
video.
a link for the next webinar, probably this
Mhm.
weekend and before the second webinar, just
Mhm.
to let you know.
Okay, you take care.
Thank you so
Yeah,
much.
thank you.
Thank
Thank
you,
Yeah.
you, doctor.
everyone.
Yes, Daniel. Bye-bye.
Thank you
Thank
so
you.
much.
Bye.
Bye.